I've summarized just the main components here.
I'm sorry.
Sorry.
The flash chip itself, not only was it designed for endurance and scalability, very, very important, which unfortunately is not here. And it's one of Bob Norman's major contributions. It was a completely new architecture for a memory chip. It was, for the first time, a chip that had a sector and a header. And the header, we had 512 bytes sector, data sector, and 64-byte header. And the header, 64 bytes, was accessible only to the controller. And it was used to manage the data in the 512 bytes. In other words, the controller had a body inside the memory chip that was used to store error correction, used to store information about this sector is no good, go somewhere else, or the last voltage that we applied here is 14.7 volts, please don't go 20 volts, things of that nature. And we want to erase in parallel these 75 sectors because it was time consuming. So the header stored all of this information, stored the number of cycles that every sector went through so that you could now do wear-out leveling. It was the hot count that was a completely new concept that would not be possible if you didn't assign 1/8 more memory, which was extremely costly to do, very wasteful, if you will.
Over-provisioning.
Yes,
Yeah.
but it's within the sector. It's just...
That's right, that's not over-provisioning, it's the overhead, pardon me. Yes.
Yes,
Yeah.
but it was a combination of the controller working with the header and storing in the header whatever it needed to keep track of which are the good sectors, which are not, and which are the replacement sectors. And it allowed us to use, we had spare sectors, we had spare quadrants, but basically the controller was able to harvest bits per wafer rather than chips per wafer. When you have to have a complete chip that is good enough, your yield, at least in the first phases of a new technology, is nothing like what you could do if you can actually harvest the 98% of the good bits on a wafer or on a chip, basically one at a time, and more importantly, manage each sector to its own specific requirements, its own voltages, its own, wear-out leveling. Mm-hmm. This was a completely revolutionary concept. No one had thought about it, and it was counterintuitive because you were adding substantial cost to the chip. In the long term, it more than paid for itself. But in the first few years, we had a lot of naysayers. Mm. Of course, garbage collection, repair of disturbed cells. You had program disturb, read disturb. The controller would have no problem. We would have a random number generator on the controller. It would go and read randomly locations. If it's under margin conditions, if it started encroaching on the margin, it would say, no problem, I'll read you and reprogram you. And that's all in the background. So low stress write and erase voltages, logical to physical mapping was critically important because one of the things that I insisted on, we had to be plug-and-play compatible with a disk drive, and we had to be transparent to the host. The host operating system knew nothing about flash, so I said, look, I want us to be host independent. All the management of flash is on the controller, and I want it to be flash transparent to the host. So that anybody's flash could work because they would just change the firmware or change their own controller hardware.
It basically made the device look like it was perfect storage.
Perfect storage, regardless from where it came from, and it could work in a Microsoft operating system, in an ARM operating system, in any operating system, because it used disk drive commands. ATA, basically it's the ATA interface, which was a disk drive standard.